I just want to say thank you, everybody, for taking the time to listen to us this morning. And John, thank you so much for coordinating this event. So far, it's been fantastic. And your presentation was great as well. So we're going to be talking today about securing the software supply chain. As we all know, open source is everywhere. For organizations and individuals, the question today is not whether you're using open source code, but what open source code you're using and how it impacts your overall security posture. As a side note, I really feel we're over-rotating on SolarWinds. SolarWinds is not the easiest attack vector, and we'll get into why later in this talk. Open source packages, we believe, are the easiest attack vector. And we'll be going into and talking today about why we believe that's the case and how we should, as a security community, look to combat these threats. So to quickly introduce ourselves, my name is Jeff Hudesman. I'm the Chief Information Security Officer at Pinwheel. We are a payroll connectivity API serving some of the largest fintechs in the space. And Pete, do you want to introduce yourself?
Sure, thanks, Jeff. I'm Pete Morgan, President and co-founder at Phylum. We are working on solving the software supply chain problem as well, and that's where part of the research and kind of subject matter came from. I've been a security researcher for about 20 years, focused on product and application security, mostly focused around hardware and software reverse engineering and exploit development. Been at a bunch of places before this, but after we kind of jumped into how the landscape of the supply chain is actually working, we kind of started into this problem in late 2019, early 2020. We've learned a lot of things that we're going to talk about here today.
So supply chain security has really been blowing up our Feedly feeds for quite some time. It's easy to feel powerless as these compromises have little to do with your company's code. So how do we address this? How do we give confidence to the board as well as our customers that we have this in control and we can adequately handle this problem? So here are just a few examples of the aforementioned news articles, and you see things from SolarWinds, Twilio, and a bunch of Node.js and a bunch of similar instances that we've all read about and heard about. So software composition analysis has really convinced us that vulnerability should be the only concern of our open source dependency footprint. And we really feel that's not the case. I mean, as CISOs and government defenders, we're also concerned about the authors of these packages, their countries of origin, spheres of influence, and other untrusted code. So it goes well beyond just the simplistic vulnerabilities. There's so much more to it, and we're going to get more into this later in this presentation. So as you can see in this slide, packages are developed by random internet strangers. I mean, sometimes there's this misconception that your developers and all these very robust controls you put in place to secure their processes, the code that they write, and everything they do day to day with training, with internal controls. That's not enough. And you're going to see later on, like exactly kind of the breakdown between locally developed code and what we kind of rely on that could very well be either untrusted or malicious in some way. So the usage of open source packages is essential for our development efforts, but we really need to tackle their associated risks in an efficient and automated way. So just looking at NPM as an example, JavaScript's package manager, in 2015, it had about 12,000 packages. It seems like a lot, but now looking at 2021, it's getting closer to 1.7 million. In a study in 2019, it was found that on average, 30% of a piece of software is written by the author. So that other 70% comes from dependencies. And that goes back to the aforementioned, like what kind of control do we have of those dependencies and how do we assess their risk, and is assessing vulnerabilities of those dependencies enough?
Yeah.
So now I'm going to pass this on to Pete, who's going to go into a little more depth about this, given his research background about the associated risks and what we as an industry can do about this.
Yeah, thinking about like this slide here, when we think about the landscape in 2015, 12,000 packages, you had an average dependency depth of like 4, meaning you might have a first level dependency and it may have another level and a third and a fourth. Now we're seeing dependency chains 30, 35, 40 levels deep, where it's very, very difficult to make heads or tails of what you're actually using and how that changes over time. As we look at the statistic on that, all of the work we're putting into securing the code that our developers write is hitting 30% of the end result code. 70% of it is coming from, as Jeff mentioned, random strangers from the internet. These could be people working at large companies. They could be great developers. And these could be hobbyist projects that come out of bootcamp grads. There's not a great way to understand the difference between those two. You can go analyze it, but this therein takes a lot of time. If we could jump to the next slide. So to kind of put this in context, using open source code has been around for a long time. The way we're using open source code has changed pretty drastically. Most of the organizations I've talked to have either completed or are on their way to building what they call like a modern development environment, something that uses a continuous integration, continuous development system, some sort of build automation where their developers can more rapidly write a piece of code. They can enforce a requirement of tests on that code. And as they check in the code to a series of repositories, those tests get automatically run and the developers can find out, did I make a mistake that breaks some other part of the application? And this allows more developers to work on different things. And you can complete feature development and releases much more quickly by splitting up that work and using automation to test all the things you're doing. Unfortunately, in the efforts of trying to build all this build automation infrastructure, we've run into a case where we've taken a whole bunch of tools that have a lot of utility when it comes to automation, but are built on top of conventions, and we just started stacking them together. And for the most part, it works okay. We don't really see all the side effects of what's happening quite yet because this is so new, and there's not a great blueprint for how to do this perfectly well yet. One of the side effects of this is as we run our builds, we try to make them reproducible. So we can have deterministic output on what happened in that build. Did something break? Can we figure out the reason why and then fix it? In that process, we install all of our dependencies. We kind of build a clean slate, set up our app, run our tests, make sure everything worked. That pulls in all these dependencies from the internet. And oftentimes in between builds, that dependency graph changes, because we may be able to define a certain set of dependencies that we're going to be using in the first, second tier. But as these dependencies change by these different people that write them on the internet, that graph changes over time, and there's very, very little we can do about it. So the code that is coming into our build environments and also running on our developer workstations is changing, and we don't have it's very tough to make heads or tails of what's going on. So jumping to the slide, if we look at kind of like an ideal case, we can still see some problems here. So React is a JavaScript package for like website design. It's probably harder to find a website that doesn't use React than to find one that does. It is like pretty ubiquitous across the industry. This is used by giant names all over the place. That package itself has thousands of direct authors that have contributed code into React. And if we walk out to React's dependencies and their dependencies, and we build a graph of all the software that you need to run React, and you do this from a developer perspective. So you can, when you install things as a developer, you get a little bit of a different set than you do in like a production website running instance. you can get nearly 7,000 possible pieces of software in that graph just for React, which is one package, just for website UI layout. So in this case, React is actually funded by Facebook. They fund the open source development to the developers and authors that manage and maintain this project. It doesn't get better. Like most open source projects, there's no funding going behind. There's a very, very, very small percentage that get any money for actual development and work. So, and our hopes is this is kind of like the ideal case. But even this, when we look at that 7,000 node graph, each of those nodes has at least one author, and that amounts to having tens of thousands of unknown authors that could be adding anything. And just remember that at any point in that graph, if someone puts in a piece of malware, someone puts in a new vulnerability, someone makes a mistake, doesn't have to be malicious, that filters down to the software that's depending on it, and our software that depends on React. And this example, of course, scales to lots and lots of other packages, but just trying to see, even in the best case scenario, how does this look? If we could jump to the next slide. So one of the major things I think it's important to keep in mind is that open source risk is more than just software vulnerabilities. And as Jeff had mentioned, I think software composition analysis came around at a time when we were kind of familiar with vulnerability scanners, and we wanted to scan for vulnerabilities in these packages because astutely we understood that there could be vulnerabilities in the software that we're not ready, and we should get our arms around that. So the SCA products pretty much basically took a catalog of all of the different vulnerabilities that were known about, things from like CVE databases and other collections of vulnerability database information. They pulled those all together in a singular repository, and then would scan package manifest files saying, if you're using package A version B, I know about these vulnerabilities, you should make sure those aren't affecting you. And then also like license misuse, and this kind of came out of the legal compliance element. It's still today a kind of a onerous challenge to figure out what licenses are being used by different pieces of open source software. And this isn't really a security risk as much as it is a operational risk or a legal risk to using software, but still something we want to think about when we're using these kind of unknown, untrusted packages, because sometimes the authors will change that license out from under you. We're detecting some behaviors that are getting kind of interesting because there's a growing discontent in the open source community where they're finding large businesses making millions and billions of dollars on top of open source software they released, and they're not getting a dollar. So they start threatening to exercise the options they have, one of them being, I'm going to change the license, you can't use this commercially. Pardon me. Next slide, please. So in order to think about open source risk, we should really think about how we're using untrusted code, because it's effectively, that's what it is. It's code someone else wrote. And previously we kind of stood on top of this, I think as a group, whether knowingly or unknowingly, we stood on top of the idea that since everyone else is looking at open source code, it'll be very easy to find vulnerabilities, and it would be very hard for anyone to get malware into this thing because everyone can look at it and someone would have figured that out. And it's kind of like that, when there's a car disabled on the side of the road, everyone thinks someone else is going to go stop and help, and that relying on that idea means no one actually does. This idea in open source code has been pretty widely debunked. We've seen a lot of incidents that kind of show that with enough eyes, not all bugs are sufficiently shallow, and malware authors have found ways to get software into things that people commonly use, and they're completely open source. So to think about this in a different light, we want to care about software vulnerabilities, and we want to care about licenses. Those are important, and we shouldn't lose sight of that. But we also have to think about larger problems like technical debt. And when you think about a graph of software that you depend on when you're running your application, looking at different nodes in that graph, or a graph dominator that has a single node that influences a downstream chain. We've run into a bunch of cases just in research of finding major pieces of software that depend on one package that most people don't really know about, and they have one author. And what happens if that author gives up in that package, or stops responding to any sort of input on fixing issues? There's this pretty significant risk to the rest of the chain of those dependencies, and this is stuff that's happening out from under us constantly. All of this is moving. So just getting some idea of the technical debt and understanding, is the software abandoned? What happens if someone removes a package? This happened in 2016, 2017 with LeftPad. It was a package in NPM that all it did was add padding to the left side of an expression. This is not a needed package. It was 11 lines of code. And the author got frustrated at the package manager and decided to remove the package, and they broke the internet for about half a day. This is not a piece of software we needed. Most people didn't even know they were using it, but this is kind of the nature of how dependencies operate. We're aware of the first tier of things that we're using. We're most likely not aware of anything beyond that first tier. Looking more deeply into things like malicious code. Now, this is kind of a challenge because, if we think back to the malware industry, we've been trying to solve that for 25 years, and with some degree of success, but all of the things happening with ransomware suggest that we still got the work cut out for us. Looking at and identifying malicious code in the open source supply chain is a tractable problem. We don't need to be 100% perfect, but we can make this sufficiently difficult that attackers will move on to something else. There's now starting to be a lot more occurrences of malware being injected into open source ecosystems. And this is becoming a problem that, well, I believe this will be a problem we're going to hear a lot more about coming up. And then finally, the author risk and reputation. So as we have these graphs of packages that we're relying on as our dependencies to go build our software, there's also graphs of authors that write these packages. And we need to start making heads or tails out of what behaviors can I know about this author to figure out, is this someone I need to worry about as being a risky person for relying on their software. Just last week, we stumbled on a package. There was a news article about a package on NPM where the author had surreptitiously put in a Chrome password stealer. So if you're a developer and you install that package, it would in the background run this Chrome password stealer and exfil your passwords out to some site on the internet. So someone noticed this, and they notified the package manager, and they delisted the package, and that's great. But that's where the event stopped. This author has dozens of other packages they maintain. And I hope that once someone sees this behavior from that author, they start seriously questioning if they should be using this author's other software. Additionally, we think that package manager should probably not allow that person to publish any more open source software, at least for a while. Or there should be some process to referee what's happening, dig into that incident. But no such thing exists today anywhere in any ecosystem whatsoever. It is the Wild West for kind of attacking organizations and not having to come in through the front door. Instead of going after like a major organization or trying to fight them on a fair playing field, where the organization definitely has an advantage here, all you have to do is go after an unknown author on GitHub that has no defenses and doesn't know they're being attacked, that sits 6, 7, 8 levels up in the dependency chain. You get access to their GitHub account. Now you can add code into their repository that manages the package they own, bump a new version, and you filter down the entire chain. And with targeted attacks on this, you don't get one organization, you get hundreds or thousands. Let's go to the next slide, please. So if we kind of think back to where we are today in the antivirus, anti-malware, well, ransomware industry now, things got a lot better for the malware industry as we started moving to cloud, as we started pulling in more data sources. And we basically moved from just looking at a binary in isolation and trying to make a determination on, is this a benign or malicious binary? And we started pulling in a lot of other indicators. Obviously, with more data, we were able to see a little bit better, maybe not perfectly quite yet. It turns out, refereeing whether the intent of code is still hard, and it will be for a long time. But when we think about the differences we have when we're trying to defend an open source supply chain, we have a ton of advantages. So we have all the source code for how these things work, and we can do a lot with that. We have the full revision history for how a project operated. And I say that with a little bit of an asterisk because you can technically rewrite Git's history, and you can use that for malicious purposes, unfortunately. So I think we're going to see attackers go there, but we can use all of that data to still inform and understand what the typical behavior of a given project operates at. We can see all the author relationships and behaviors. This is all done in the public. The package metadata, the package relationships, there's a ton of data out here that we can use to kind of get a fingerprint for how quality software projects operate and use to better inform us when something deviates. If we jump to the next slide. So the challenge here is when we kind of think about how to analyze this and how to work with developers on it, it's a little bit of a different challenge than doing vulnerability triage or vulnerability management. Typically, when we scan for vulnerabilities, we try to find an artifact that confirms the presence of a operation, behavior, or piece of code. Once we see that thing, we write that because we know this is a bad thing. We build a check for it. Once we scan and can detect that check, we can have confirmation this vulnerability is there. Now we have to figure out what do we do about it. Supply chain risks are a little bit more gray, and they're almost always multifaceted. There's very, very few instances where a single indicator can tell you everything you need to know about a supply chain risk, because there's so many different moving parts on how these all operate. So we need to be able to take in all of this data and start analyzing at a different level and a deeper level. We need to be able to pull in these indicators and connect them together, kind of like a detective, in order to figure out what is happening and where these risk indicators are rising to a level where we need to start acting on it. There's a significant risk here of kind of building a bunch of tooling to start digging into the supply chain and just dousing our developers with way too much information to the point where we're going to lose them. I've talked to a lot of customers where we've seen this happen. I've talked to a lot of friends that really get frustrated with the kind of security research tooling community because it has like limited value in a singular area and doesn't really apply to them, but makes their life significantly worse. So I think as we're building new research into this area, we really need to think about the audience that this is going to. There are things we can do to say that's a really cool piece of work or that's a really cool piece of research. But if we can't get this into developers' hands and make it actionable to them in a quick fashion, we're going to lose. There's simply too much open source software out there. We were looking at just kind of a cursory study of how many packages in total. And if I remember correctly, it's somewhere around 160 million, because we have to account for version differences in semantic versioning and how these graphs get built. And that's just untenable if we start alerting developers on even a singular percentage of that. Let's jump to the next slide, please. Yeah, type of squatting. So I want to dig into one attack just a little bit. This one is in the news quite a bit. Hopefully, hopefully someone here has heard of type of squatting before. This is an attack where I, as an attacker, might want to. I'm trying to get a watering hole style attack. So I might see that Babel-CLI is a super popular package that lots and lots of people use. And previous experience has told us that humans don't really remember names well, and they don't always type perfectly. So I'm going to take the software from Babel-CLI, download it, and then I'm going to rehost it with a very similar name, maybe Bagel-CLI, or I'll drop the L, or I'll drop the dash. And just doing that, I will get thousands and thousands of downloads a week from people typing the wrong thing or misremembering a name. This is an extremely effective attack. And it kind of preys on elements of humans making mistakes that we're probably not going to fix anytime soon. But what's effectively happened is now they're relying on my software, not the one they intended. And any changes I feel like making in the future and bump the version number will filter down to the people that are depending on my package. And this is the problem with typo squatting. At that point in time, I, as the maintainer of that package they're mistakenly using, can change out that code, drop in malware, put in a backdoor, the vulnerability, and I have code execution on their developers and their build infrastructure. And remember in this case that developers have grown to be one of the best targets, especially in this remote work culture. They have the keys to everything. They are most likely to not have the advanced defenses turned on because it will frustrate them and slow down build processes. So they are the crown jewel for what attackers are going for now. And this gives me a shortcut path right into a developer. And this isn't like hypothetical. There's thousands and thousands of packages that are taken down a year for typo squatting. But this is another one of those attacks that seems kind of like a little bit interesting at first, but when you see the scale of it and how easy it is for an attacker to kind of automate this style attack, it gets really scary. Let's jump forward. So, yeah, Jeff, do you wanted to hand it back over to you?
No, Pete, I think you could take this one if that's cool.
Sure. So, one thing that I think I hate to be all doom and gloom when it comes to talking about some of the new work we're seeing and some of the new areas we're jumping into, and that's unfortunately an artifact of security research that is very, very common. We start digging into an area, we find out there's some new things we didn't know about, and we want to bring them to light so there's understanding and we can start working on the problem. But often it means, freaking people out or scaring people, and that's not really a positive thing. One of the benefits here is that security automation really gives us a chance. So as organizations move to these CI/CD systems, we really want to, I think we need to see this happen intentionally and carefully, and hopefully with a little bit of better plan, and we can work to figure that out. But the automation really gives us an opportunity. If I look back to my consulting background from years ago, I've worked with thousands of companies over the years that we wanted to come in and audit some source code and figure out were there bugs in this product. So we had to wait until it was relatively feature complete, or at least security feature complete, before doing most of our work. And that meant security had to come in at the end or close to the end of the software development process and do our work and then bring those bugs back and then try to figure out how long would it take for them to fix that. And that often ended up changing timelines, and I'm sure lots of people here are familiar with that kind of engagement. It was very problematic to everyone involved. Security we didn't get enough time to do the quality of work we wanted to, hardly ever, because it's a challenge. And the people managing the product were frustrated because they had timelines they wanted to hit. Then they maybe accounted for some time for security defects to be fixed, but if that goes over, now product timelines push and the rest of the business kind of suffers. Looking forward to today, we have lots and lots of automation where we're not building software kind of in a vacuum and then testing it. We can do this piecemeal as developers are writing new features. As pull requests and merge requests come in, we can see elements of code, we can run our unit tests, we can have full integration tests, and we have an opportunity to run security tests in this automation. And we're starting to see more and more tooling and more organizations build programs around this concept. And I think it's going to be hugely beneficial, because as we get our arms around this better, we'll be able to have more complete testing done on both a verification but also security side, in an automated context. So at the end, we're not left in that same state where a report gets dropped and we have to kind of, move everything around in order to kind of deal with it. So I think that seeing how this the automation landscape is really moving, there's going to be a ton of value for organizations to leverage those opportunities to build security into their pipelines. And we see your DevSecOps is all the rage right now. But I don't know if I'm over time. Yeah. I can probably wrap there.
We have no, we have till 10:45.
Oh, very good. Okay. Yeah, so I just wanted to mention that this is not the challenges here in the supply chain, I think, are mostly going to be centered around the CI/CD processes and thinking about it, thinking intentionally about what our automation is doing. There's going to be, and just to harken a little bit of a dark future, it's going to get worse before it gets better, because this is just too new of an area. And looking back over kind of a long career, we make shifts and then we compensate for the deficiencies we didn't know about. And just now we're starting to see more research come out that is focusing on these new areas in the DevOps pipeline. And literally this week, I think Monday, I saw on something, a great piece of work where a researcher figured out that using GitHub Actions, you could bypass branch protection. What that means is, what if Jeff and I are working on a piece of software together, if we're trying to be very careful about things, I can't just commit directly into the main branch or the main branch, and Jeff can't either. I have to write a piece of code and send a pull request, and then Jeff would read it and say, okay, I like this, and I'll accept it. It's one of the fundamental things that protects how we develop source code today. And someone just found a bypass around that. So if you have any write access to a repository in GitHub, you can bypass that branch protection, which is like the fundamental control behind this. And this is a great piece of work, and we need more of this research because, again, we've moved so quickly into relying on this new set of technologies that I think are going to push us forward in great ways, but the research hasn't yet caught up, and we are going to see more and more in this area. And I just I'd like to say that because it's important, it's going to happen, it's an inevitability, but it shouldn't discourage us from pushing the security automation landscape. This is going to be a really important thing. I'm starting to see some questions. Should we move into Q&A?
Sure, let's do that. Let's see. I will ask. There's one from Yolanda. Can you touch on auditing the configuration of machines? This is in respect to data exfiltration. In this case, the R&D servers at Bettis Atomic Power Lab, a government-owned facility by the U.S. Navy, where Navy engineer Jonathan Tebb was able to download to SD cards.
Yeah. So on auditing the configuration of machines, this is actually, it took a second for me to connect it, but yeah, this is definitely a supply chain problem as well. This is something where, if we think about, we were talking mostly about open source packages today because this is kind of like the low-hanging fruit, in our opinion. But if we shift the lens a little bit and think about kind of infrastructure as code, which has really exploded, and it's a great idea. We're managing the configuration of our machines most often now in GitHub and GitLab, basically with a Git backend, so we can track the state and the configuration, understand the changes, revert if we need to. So there's an entire series of tooling that is kind of sprouted up around that to help us understand what's happening on this infrastructure as code. This could be Docker containers, these could be Terraform scripts, and a whole host of other things. One of the issues there is we need to solve the code provenance problem. And that is, where did this code come from? Where did this infrastructure as code come from? Who wrote it? What did they do to it? And how did it get to the state that we're using it today? Without knowledge of that, the best we can do is kind of use these wide berth rules that we write after the fact, after we discover something's wrong or someone, there was an issue, and we're going to write a rule to fix it so it doesn't happen again. And that's better than nothing, but it leaves us in kind of that late 90s, early 2000s antivirus state where they write a definition for a virus after they see it, and then you're protected. But it doesn't stop anything from hitting you the first time. So we need to get the code provenance problem solved to get our arms around that better.
Cool. So there's two questions here that are similar. What should open source repositories be responsible for deploying SAST on committed code? And what do you think that is different from the likes of White Source and Sonatype to check the validity of code downloaded from these repositories?
Sure. First, I'll take the open source repository SAST. In a perfect world, that'd be wonderful. If SAST was free and it worked really, really well, that would be great. We could move the needle quite far. The other thing to remember is these open source repositories are made by volunteers. In 99.9% of cases, they're not paid for this. They get no credit for it. The best they can do is say, I have a package that other people use, and they kind of put that on their resume as being as a developer. So hoping that we can put more requirements on these volunteers on the internet to do better is not going to be a tenable defense mechanism. We have to find a way to both understand the code that we're pulling in and hopefully, where possible, incentivize better behavior or better operational behavior from these developers. Right now, again, it's we don't have a lot of arrows in the quiver to do that, because their first thing they'll say is, if you want better behavior, pay me. And there's been a number of attempts to try to operationalize that, but they really haven't hit in any sort of large way. What do you do? What do you do that is different from like Sonatype or White Source and Sonatype to check validity?
I think that's a vendor-based
Yeah,
question.
that's more of a vendor question. Yeah, let's I'd love to talk about that, but not here. What are your thoughts around SBOM with regard to both technical debt and security posture? Yeah, great question. Thank you for bringing that up. SBOM is stuff I've been hearing a lot about lately, and it reminds me, like, I've seen this pattern before earlier in my career, where SBOM is a great thing. We should force people to generate a software bill of materials so we understand the components that go into a piece of software. But the thing I always struggle with is, once you have an SBOM, then what are you going to do with it? An SBOM should be a living document. It should be the input into a living system that understands at a risk level what those components are, because those are things that we're relying on for our software to operate properly. We think about risks of the code we write and the systems that we manage, and there's been a ton of work on really understanding it at a deep level and running that efficiently. But this SBOM work is kind of what gets us into thinking about the third-party components that we rely on. That could be open source software, that could be other pieces of software we buy and use. But as that graphic kind of showed, there's 70%. This is a huge part of the problem, and it's an element that having a much bigger security budget doesn't automatically solve. We can't pay all of the open source developers that manage the packages that we write to be better or to do the things we want. It's not a tractable problem. We have to find a different way to think about the way we're interacting with things that we rely on. On the theme of ransomware, should we be contractually obligating suppliers to notify our clients when a breach occurs, or more specifically how to handle the ransomware? It's an interesting question. I don't know if I'm a good person to answer that.
No worries. There's another question in the chat. Can you mention your thoughts about IT security, including IT security auditors in their testing of implementations?
Yeah, this is something I think we're going to see a lot more of, and I think it's a good thing. doing more consultative security review work on our development environments and these automation environments that we're using to build software is going to be very, very important. It's not really well defined yet, and I don't think there's like a lot of service offerings from pen test shops or red team shops or even IT auditor groups for figuring out how to do this yet, but it's going to grow because it's a necessity. The attack surface is way too large, and as I mentioned before, talking to lots and lots of different groups about this over the last few years, there's not a blueprint for how to do this right. I've also never come across, when I'm talking to customers, I've never come across two customers that are using exactly the same configuration ever. There's too many pieces that you can fit in to kind of build your own flavor of how this works, which can be great, but it also means there's gaps in the conventions of how these things are used. Not a lot of rules, but lots of conventions. And those gaps are where attackers find foothold and can do interesting things.
Great. Okay, so this question is the differences in generic sense without saying which vendor does what.
Sure. Yeah. So I think it's easiest to kind of look at the lineage of where tools kind of came from. And this isn't unique to SCA tools or the supply chain space. You can see a similar lineage in like vulnerability scanners and anti-malware products. But we start out doing something to try to improve the state of the art and make it harder for attackers to win, make it easier for us to defend. And then we kind of iterate on top of that. And I remember, if you remember downloading virus signatures all the time, right? Like these were just databases of hashes and file fragments that we could then use to stop known viruses. And that's kind of pretty similar to what the SCA tools are by and large doing about vulnerabilities. One of the, if you can solve the halting problem, we might be able to start understanding more about automating the vulnerability discovery at a complete level. We can't do that, so we have to rely on humans to identify and confirm vulnerabilities before we start operating them. That means we're only limited to the set of things that humans can find. We glanced at some data the other day. I'm just trying to remember this specifically. I think in 2008, 2009, GitHub had 100,000 repositories. And today it has like well over 200 million. In 2008, 2009, I think the CVE database had like 5,000 bugs, ballpark, 5,500. And it's grown by like 10 or 15,000 a year on average, something like that. So if we think about it and we just look at those numbers, either developers got like 1,000 times better and produced 1,000 times less bugs based on the quantity of code, or we just have no idea how deep these bugs, how many bugs there really are, because the amount of code produced has completely outpaced our ability to analyze it and referee that. So taking that into account, this is where it becomes a big struggle for some of the SCA products, because we're hoping that humans are fast enough to detect these bugs, but it's pretty clear it's not.